You guys are very
Tens of thousands of
easily
people lined the
entertained.
banks of Kiamtang River early on Monday morning to watch a single sweeping giant wave or tidal bore. It happens when the tide flows upstream against a river's currents. Coinciding with China's traditional Mid-Autumn Festival, the annual tidal bore is one of the largest in the world and can reach up to 9 meters in height, speeding at up to 40 kilometers per hour.
40 kilometers an hour. So this is interesting too. So we know something about the velocity, right? Square root g times depth, right? Gravity times depth. So hopefully we know something about that. Where's it gone?
More than 30 people were injured as a large tidal bore crashed with great force into the bank of a river near the city of Haining in China. Given extra impetus by a typhoon, the huge and powerful tidal wave gathered momentum with alarming speed. People were heard screaming and many ran for cover. A local observation station monitored waves as high as 20 meters, apparently the highest record in a decade. The impact of the massive water invasion destroyed the wave wall and the protection net along the river. The injured were taken to hospital. No deaths were reported.
So that's from a year ago. The first one was this year, just a couple of days ago. Why is that? Why should they be this time of year? Oh, we don't do this. Okay, turn the music off on this. So tidal bores are driven by tides, and so it's a high tide when you have a full moon. It's a full moon. If you looked outside, I think it was a full moon on Monday night, and so full moon means that it's in the opposite side of the Earth from the sun. Hence, it's getting it's fully illuminated by the sun, and therefore all of the pull of the sun and the moon are in alignment, and hence the tides are large. And so the tidal bores, which exist at a variety of locations around the world, are largest because the tides are large. So this one is in China, the first one. This is actually some video of the Bay of Fundy, which is up, begins at Maine. It's the bottleneck that opens up in eastern Canada. And as we said before, when we were talking about wave velocities, celerity wave velocities, the idea is that the shape of the bay, which is probably 600 kilometers, a few hundred kilometers long anyway, and its depth are such that the resonant frequency for the water in that vessel, just like blowing across the top of a bottle, is such that if you give it a 12-hour forcing with tides, then it resonates. And so you also get tidal bores going up the rivers on the Bay of Fundy. And Bay of Fundy happens to have much larger tides than, well, the largest tides in the world. So probably of the order of 30 feet, 10 meters, between one tidal change. And so places like St. John, New Brunswick, I don't know if it's St. John or St. John's. St. John's, Newfoundland, and St. John, New Brunswick. I always get them mixed up. But St. John, New Brunswick, which is close to the top of the Bay of Fundy, has a waterfall that reverses. Water flows into the bay at low tide. When the tide comes up, then the waterfall reverses, and the estuary water, brackish estuary water, seawater, flows up into the river. And so this is somewhere in the Bay of Fundy, and this is not such a clean tidal bore as we saw in the other places, but these are kind of whitewater rapids, like whitewater rapids, which exist because there's this wave that's trying to generate itself up the river. So, anyway. So that's our off-topic interlude. Well, not off-topic because it's still fluids, of course. We know something about the velocity of these waves. They're the square root of the depth times gravity, as we learned maybe a couple of weeks ago. And the mechanism for them is widespread resonance. So they're actually quite significant waves as you try and get this large volume of water to move in from the mouth of this bay all the way up to the top and then back again in a 12-hour period. Not physically moving those 300 kilometers, but like the train wreck, you hit one car, the next car hits the next car, and its effect is felt at the top of the bay. Okay, so we'll leave it at that. All right, so enough joy for today. So get back to our activities. As of today, let's see what's. I'll stop that in case it's overriding it. As of today, you are in teams, and so the it keeps on doing this. Don't make it do this. FKD. Interesting email address ID, don't you think? So as of now, you all have are in teams. So the next thing that you have to do, of course, there'll be an assignment due on Thursday. The assignment will be on the previous material on last week, fluid pressures at a point. So don't forget that. The other activity that you should do is you should contact your group mates, and to contact your group mates, what you might do, I don't know who is in Team 1, but this is what you should see. And so, yeah, this is exactly what you should see. So homework 2 are live now. So what you should do is you should contact your group mates to be able to set up a meeting. It can be an online meeting or phone meeting or a face-to-face meeting, probably is best. Probably the easiest way to contact them is to send them a message on Angel. And it's showing me here all the groups. I should be able to send everything to my group, which I'm taking as group 1. So a team will come up here that you are in. And you should be able to join that. It's just, I've already done it once. I guess I won't do it twice. I guess, well, perhaps it'll go to twice. So I'm going to send it. And so you can just say hi. So, as far as I know, that's one way to get hold of your teammates. So, Team 1, whoever they are, will be getting an email from this, and it'll go to all 4 or 5 members. So, we have 310-ish people in this class. We have 62 groups of 5-ish. Must be probably some groups of 6. I don't know. I think neither Nick or myself or Ferry are in any of the groups. Some people may drop or add the class, and so groups might get adjusted as we go along. But do meet with your groups or make connections with your groups. Decide on a topic by, is it October the 10th? So I'll ask Nick to send out the stuff on the rubric for the assignment, the examples for the assignment, and maybe in the past the TA's also downloaded a spreadsheet of all the teams, so you can find out which team you're in and what your other group members are, because I'm not, or otherwise find out how to do that for the students. So it's nice not just to be able to send an email to kind of the ether and not knowing who you're going to, because invariably you won't hear back from some of your colleagues, and you need to kind of force that. I'm reminded of a juvenile joke I saw online the other day. It said, when I die, I want all the people I've served on team projects with me to come to my funeral so that they can let me down into the earth one more time. And so that's invariably true for this. Some people won't perform. And so perhaps we should also send out the peer review rubric. And so there's a peer review that each of you in your group will complete on each of you and yourself and your other colleagues to say what the performances were, both of yourself and your colleagues, and grade it out of 20 for attending meetings, contributing ideas, etc. And so for those who don't participate, there is a downside, which it should be, and so there is an upside for those people who do put in good effort. And so that's kind of where we are right now. So any questions on that? You have almost a month to do this, but it's going to be first come, first served to load up a topic who will get that topic. So invariably there'll be a lot of people who want to do, why do we spin a football? Why does a golf ball have dimples? Why does a baseball spin? And why does a bullet spin, etc. And so first up, we won't have people doing the same thing. And so if you're a second person to the gate wanting to do one of those things, then you'll be excluded. You'll be asked to change. Yeah. The groups are posted on Angel, but you can't get them. You can mail them in the way I just did. It's okay. But Nick, maybe if you can run off the group membership and send an Excel spreadsheet. I don't think it's a breach of confidentiality, right, for you to know who's in your groups and who the other groups are. And so we've done that in the past. Okay. So anyway, so look for an email. You have a month to do it, so it's not urgent to be able to do it today, but you should put things in motion to be able to maybe do that. Okay? Any questions from last time before we get going? Okay? All right. Okay. What were we talking about last time? We were talking about pressures at a point. Don't know why it doesn't want me to do this, and I'm going to draw some things just because I can. So, all right. So, just a recap from last time. I'll write it rather than do anything else. It's week 3. It's the second period. Fluid pressures. Actually, forces as well, right? On structures. And we'll recap the 3 things that we've talked about. And you remember we made 3 points that we'd like to be able to do. We'd like to be able to calculate the magnitude of a resultant. And so if we have a very simple, let's draw a very simple structure, and that structure is going to be just a straight wall that has a water level in it, that has a hinge at the bottom, that we want to apply a force, I'm going to call it force 0 because I just want to. And so that's the system that we want to look at. And we said last time that if we look, for instance, at the pressure distribution for this surface, that so far we've only drawn pressure distributions for things that intersect the surface. And if you like numbers, let's just put a number on this, and let's do it 1 meter into the page. And so what we'd like to do is to figure out what the force is, F0, that we have to put on this to be able to hold this wall in place. Simple desire. It's water that's behind it in the system. And so we said that the magnitude of the resultant is, we'll call the resultant FR, which is equal to the area of our wall or our plane surface times the unit weight times the height, the depth of the centroid. If we draw our wall to scale or in perspective as we had done before, and we figure out the centroid, this in our system from the surface is the height of the centroid. And so we can put numbers on all of that. We know exactly where that is. No one reclaimed their prop that we're using. And so this is our wall. Force here, water on the left-hand side, pushing it over, hinged at the bottom. If we don't have a force at the top, it'll flop over. What force do we apply? Nothing more than that. So the magnitude of the force we can work out, and it's going to be equal to what? The area is going to be 10 meters squared. The unit weight is going to be 9.81 kilonewtons per meter squared, per meter cubed rather, and we're going to have to multiply it by depth of centroid times 5 meters. And so that is going to be of the order of, not the order, I'm going to use this 10, so 10 times 10 is 100, so it's 500 times 10 to the 3 newtons, kilonewtons, right? If you work out. So meters squared, meters cross out with meters cubed, etc. So we know the magnitude of the resultant, which acts across here. 2. Where does the resultant act? And for this particular job, we're going to call this y sub r. And y sub r is just going to be the depth down to where this acts. And we did a quick derivation last time. We made the case that the resultant acts, in this particular case, at the centroid of the pressure distribution. So you take this triangle, you find its balance point, and see where it is. We did an analogous calculation. And in this particular case, if this is equal to h, so in this particular case, yr is equal to 2/3 of h, which is equal to 6.66 meters. So we know where that is. Beware that that exists only for the case where we did this simple calculation last time, but we can do it. And the third point that we wanted to be able to make was resolve a failure mode. And so the failure mode is, how is this gate going to fail? And so it could be that it slides along the base, in which we resolve horizontally, and we don't need to know the location of the resultant. But for our particular choice, we're going to let it flop, and we can just resolve moments. So we can define moments around the failure point. So that's very important. If you remember last time, when we did part 2, we resolved some moments around a random point. It happened to be the surface, and we could calculate the location of action of the resultant. And we could have chosen any point. We happen to choose a surface. If we're looking at failure, we have to resolve moments, if it's a moment problem, around the appropriate failure mechanism. And so if we're doing this, so if we sum moments, that would be what? The clockwise moment would be around this point, so it would be 1/3 times h multiplied by fr. And that has to equal h times f0. And so if we divide both sides through by h, we have our result. So it's, in other words, f0 is equal to 1/3 fr. And so it's equal to 166.6 times 10 to the 3 newtons, is that right? Yeah. So this should be f0 is equal to 166.66. Is that 1/3 of that? Times 10 to the 3 newtons. Everything right? Sometimes I screw up, but I'm not sure. Often I screw up. So that's the simple calculation. So remember those 3 cycles. 1, magnitude of the resultant force. 1 to know, secondly, where it acts. And then if we know where all the forces on a structure act, we can resolve them around some failure mechanism, which has to be the failure mechanism to be able to figure out exactly what the restoring force is or what the design force we have to apply to be able to keep this thing standing up. So that's our mantra. The other reminder maybe is that although this expression is always correct, always, for everything we do, this is the centroid of the plate on which it acts. This expression is only true now for this very simple plane square geometry. So we'll do something now to resolve the fact that we don't know how to quite get yr. for every single system that we'd like to choose. Okay, so that's where we're going.
Question?
Yes, go ahead.
When you say simple, what exactly do you mean by that? Do you mean that we don't count the shearing stress or something like that?
By simple, I mean that for YR, you mean?
Yes.
For YR, I mean simple in that the structure is a rectangle and that it intersects the surface. That's what I mean. That's what I mean. That's specifically what I mean by simple. So if the conditions that we applied in our derivation are that this intersects the surface, the water surface, could be above it, and then we wouldn't care about the part above it, right? And that it's of unit width, same width. That's all. Those two conditions. Good question. Yeah. 500 times 10 to the 3 newtons? Is that not right? Oh, because it is, so all I've done is I've taken, this is 10 meters squared, which is 10 meters by 1 meter. This is 9.8, so I guess I'm just making this 10. And I'm multiplying it by this number here, which is on the bottom. So area, unit weight, times the depth of the centroid, which is half the height. So 10 times 10 times 5 is 500. And then this is kilonewtons. And so all I've done is switch kilonewtons. So we could also write this as 500 kilonewtons, right? So that's all. So I just switched those out. Okay. All right. So what do we do now then if we do the not simple case where we have the condition to deal with something else? And so you see that this is now the case that we're dealing with. We've just gone through this example. And so I'm not really interested so much in this derivation, but we'll go through the derivation. But we'll make the case that the final result of this derivation is the important part. So here's what we're going to do. You remember that last time to get this 2/3 component to define the distance from the surface that resultant acts, we basically took, we equated that the sum of moments had to equal the resultant force times the location where it acted. So this is just the moment is equal to a force multiplied by a lever arm. It happened to be that we used this triangular distribution. We used this as our rotation point. We used FR as here. And we wanted to calculate YR. And so we figured out exactly what the moment was that we had to apply to be able to do that. And that's what we'll do again. So what we can do is we can calculate the moment due to the pressure distribution by taking an inclined plate. It happens to have kind of an irregular section if you look at the profile of it. So in other words, it's this, just with a cutout in it. So it's not a full plate. It's of some random geometry. And we know that the force that's applied is equal to the unit weight times the area of the plate multiplied by the depth of the centroid below the surface. This is no different from what we had before. All we're doing is we're writing the depth of the centroid below the surface vertically as a distance that is in the plane of the plate, which is y sub c. So this is the centroid, this is y sub c, and so if you like, y sub c sine theta, this is theta, is just this distance. So it's no different from what we had before. So this is the expression we had before for the resultant force. If we take a small change in this, take a derivative, what changes? The force will change if we take a small area. So instead of taking the whole plate, we're going to take a small area, and that area will just be of some, what we had before as some length dy times dw, I guess, but we're not going to split it up like that. We're just going to write it like this. And so what we can do is, since we know that the resultant force multiplied by the location where that resultant acts has to equal the moment due to the distributed force of every single point along that plane. So a small force here, a larger force here, larger and larger and larger as we get deeper and deeper. Then the expression for that is just this, the change in the force for every little area of increment multiplied by y. And so if we take this expression here and we write it as this, y we can get for every point, and we already just defined what this derivative is. And so if we substitute this in, we end up with these components. So we have this defined now as a function of all these differential components, and for general geometry that's not now vertical but is inclined. And so what we can now do is we could take this expression and we could divide both sides through by FR. And if we do that, we have this defined as a function of this, and we know what FR is as well, right? We know what this is. And so let's take those two things. This part here, we have right here. This part here, we have right here, and we're going to combine them together. And if we combine them together, we get this expression just here. So this is something we've seen before, right? Unit weight of the fluid, the area of which it acts, times this is just h sub c, the depth of the centroid of the plate. And this is our new expression here that we've just got from this kind of complicated derivative. But you see that we can get rid of a bunch of these terms. This cancels out. And if we do that, we end up with a kind of a complicated expression, but one that says something about how we'll use this. It allows us to calculate the depth of action of these forces for absolutely any geometry, any plate we have, any shape, any inclination, and any depth below the surface, intersecting the surface as well as below the surface. And so it's the most general expression we'll have. And by definition, this term on the top, this integral, which we rarely have to calculate because we can use standard results for it, is called the second moment of area about the surface. So this term here is called the second moment of area about the surface. And all it means is a very fancy way of saying if you take a lever arm of something against the surface, then this would just be equal to the sum of the lever arm multiplied by the force that's applied and resolved for every single point on this. So it's not very convenient for us to be able to calculate this y squared term for every single geometry we have. So what we do is something different. Instead of doing it about the surface, we use a standard result for when this point of rotation, where the pressure begins, right, and varies linearly with depth, this point of rotation we take to go through the centroid of the plate. And if we do it through the centroid of the plate, what we can do is we can rewrite this expression, which is kind of complicated here, and would require us to calculate it for every single case we did. We can replace it by a surrogate. And this surrogate expression has two parts. It has this new part, which is defined as so you might have seen this in your dynamics courses, moments of inertia. It's basically the same idea. Second moment of area about the surface is kind of the same as a moment of inertia. And this is called the second moment of area about the x-axis and through the centroid. So that's it. And through the centroid. So x-axis is, so I'm blowing away our rules. X-axis is my thumb on the surface, y-axis is in the plane of the plate. So what was happening before is this, it's the moment of inertia about this because the pressure is linearly varying and increasing with depth. What we've done is we've taken the x-axis and we put it through the centroid of the plate, and now so it's this rotation here. And so this is a standard result that we can use for a plate, for a circle, for a half circle, for all kinds of shapes. So we can get this result for IXC, and then we only need to have this other term. And so the other term is the area times the depth of this centroid along the line. So Y sub C is the distance from my thumb to the centroid. So I can't do it because I don't have an extra hand. I could do it like this. This is the distance from here to here. Right? That's all. And you'll see that as we go down a page. So the bottom line is we can always calculate the depth to the where the force acts as a function of a standard result if we know where the centroid is relative to the surface and if we know the area of the plate. That's it. Okay? So that's an important result. You can, if you feel, there's another exposition, if you like, of that calculation right here. This is actually a useful diagram, right? This one here. And so these are all the terms that we've talked about. So IXC is a standard result, which we'll see how we get in a second. The area is this area of this plate. Y sub C is the distance in the plane of the plate to the centroid of the plate. Shortest distance to the surface. X-axis is on the surface. So this is on the surface. And that's it. So those are the things. So what you can see from this, actually if you write this in a slightly different way, if you write it as YR, exactly the same expression, is equal to this term, so this is exactly the same expression. This is a useful way to write it because it says something about it. It says that the force is going to act at a point. This is the center of pressure. And the center of pressure is where this resultant acts. The resultant is given by the unit weight times the area times h sub c. H sub c is the vertical distance from the surface to the centroid of the plate. Easy to get, right? We can do that for any system. And the place where it acts is equal to the location of the centroid of the plate, which is y sub c, plus a small amount. And so what it tells us is that the point of action of a force is always going to be below the point at which the centroid is of the plate, always. It can migrate up to the point where the centroid is if it's very deep, but it's always going to be below it by a small amount. And so that's a useful result for us to have. Okay? So we're not going to ask you to derive that, but we are going to ask you to use it in different cases. Okay, so here's a quick example to go through. Just take it on trust that we can use it. I guess the other thing I haven't shown you yet, but let's zoom through to this, is that the standard result that we're talking about are moments of inertia or second moments of area. And so you've probably seen these in your past. These are standard results. So the term we're looking at is the first moment of area, second moment of area about the x-axis and through the centroid. And so it's just a number. It's just, for this particular case of a plate, it's the width of the plate multiplied by the height of the plate cubed. And basically what it's doing is it's taking the centroid of this plate, which of course is in its middle, and it's looking at the ability for this plate to, if you had to spin this and it had some weight to it, it would say how much inertia was in this plate. That's the other kind of mechanics explanation of this term. We're using it slightly differently. And so you'll see here the area of the plate, of course, you know, is just the product of the two lengths. The moment of inertia is, I've just blotted it out, so maybe I should go back and get rid of that so we can actually see it because we'll use it. We typically won't use this one, but we might use this one. And this is the second moment of area about the y-axis, this direction now, for something that goes through here with a pressure distribution that varies with y. It's a bit more complicated, but let's go through an example to cement those ideas. So the two things we'll use will be these. The first question we'll do will be for a circle. And so the first moment of area, sorry, the second moment of area or the moment of inertia for a circle is given by pi r to the 4 over 4. So remember that. And also remember that this is 0. This is basically saying that this is 0, is that if you have this stuck in water, irrespective of its orientation, the pressure acting on this side of the middle and the pressure acting on this side of the middle exactly balance each other out because of symmetry. That's really what it's saying. And so the point of action would be through the line that goes through the centroid in this particular arrangement, although it might not be at mid-height because of this linearly varying pressure distribution. Okay. All right, so it's just an application of this. So here's the application. So we have a gate, happens to be a circular gate. It's a plain example, so it's like a coin. And so what we want to do is we want to calculate the magnitude of the force that acts on this plate, because what we're going to do is we're going to assume that this plate is a washer that has a shaft through the middle of it, and it acts as a gate. And when the pressure is acting on the bottom, it will try and push this gate this way if there's nothing on the right-hand side, and you have to apply a stop to it to be able to stop it. So our question is going to be, how much force do we have to apply here to be able to stop it from opening? Okay? So we'll do the three things that we've talked about. We want to calculate where the force acts first. So we're doing the second one first. So the force acts at a distance below the surface, y sub r, which is given by the second moment of area divided by the depth of the centroid. And in this case, it is the depth of the centroid because it's a vertical plate, and the area. So what's this? This term here is the term we just pulled off. The second moment of area. What's the depth of the centroid? Well, the centroid of a circle is where? It's midpoint. Centroid of the circle is 10 meters deep below the surface. Everything's measured from this coordinate system. X is on the surface of the water. Y is vertically down, through the plate. In our case, the plate is there, so Y is vertically down. If the plate was inclined, Y would be in the plane of the plate. So we have those terms, and we have the depth of the centroid, which is also equal to 10 meters. So if we know the radius is 5 meters, I guess. The diameter is 10 meters, so the radius is 5 meters. So we have everything we need to be able to calculate that. And I'll let you go through the calculation, but it's just using those terms. It's important to understand the geometry and how we use those terms. And so, lo and behold, what comes out is that the depth at which this force acts is equal to 10 meters, which is this is YC, Y sub C, the depth of the centroid, this point here, plus a small amount, 25 over 40. So 25 over 40 is, well, it's 0.62. Actually, it's 0.625, isn't it? Whoops. Bless you. Bless you again. So we calculate. So it's equal to the depth of the centroid and a bit more. And the reason it's a bit more than the depth of the centroid is because of this. If you looked at this distribution here and looked at the midpoint, then you have a larger force acting on the bottom part than you do on the top. And so if you resolved around the middle of this portion here, you'd find out that this moment was larger. And so the balance point of this is below that. If you like, this point of action of the center of pressure is the neutral point along this plate, where if you apply a force, the force acting below it times its location, and the force acting above it, split in either way, would be exactly neutral. They would give you no net moment. And so you can see in this place, the reason that it's below the midpoint is because you have this slightly larger pressure distribution, this area here, acting below it, than you do have acting above it. So that's the basic reason. So it will always be larger than below the centroid, always, or it could be equal to it. In this case, it's below it by 0.6 of a meter. We could calculate the location. We haven't derived this equation. Let's not derive it. Where does the resultant act in the x direction. So remember, our plate is here. My thumb is the x direction on the surface. And so not only can it rotate this way, but we could take moments about it this way. You know from the geometry, you can imagine that because the distributions as two stripes getting higher pressures as you go down here are identical on both sides, there'll be no net moment around the center axis. And the exposition of that is this term here, where we do have an analogous expression to what we had before. Look, this is exactly the same as this, except we've swapped out the value for this second moment of area. And as we said before, this second moment of area is equal to 0. And that's just an indication of the fact of the symmetry of this thing. You've got as much stuff trying to twist it this way on one side as you do on the other side. Even though the distributions are linearly varying in depth, they'll be identical on either side as two stripes. And so the value of this term is 0. And when you add that term into this, if this is 0, then the location of action is the centroid. So now we know exactly where it acts. I should have brought a round thing in. We know that it acts 10.62 meters in an inclined direction down here, and it acts dead in the center of the circle. And so we don't need to know this one, but we can get it from this. So we've got the first part. We've done it bass-ackwards. So we've got the first part, which is, we've got the second part, which is where does it act? How big is the resultant force? Unit weight, depth of the centroid, times the area. Unit weight is 9.81 kilonewtons per meter cubed. The height of the depth of the centroid is 10 meters. And the area of the plate is just pi r squared. Pi d squared upon 4. So this here is 10 meters. And if you do the calculation, you get a force that acts. So we have two parts. We've got a force, we know where it acts, and so we can do our stability calculation. So stability calculation, straightforwardly, is to, this is the side view, this is kind of an isometric view. So this is the shaft that goes through the circular gate. It's like a butterfly valve on a carburetor, if any of you know what a carburetor still looks like. Not in vogue these days, I guess, with injection, fuel injection. And so it rotates around here. If it's filled with water on both sides, then the force acting on the left side would be exactly equal to the force on the right side. Just dunk it in water, just sit there, right? Irrespective of this. Take the water away from the right-hand side, then all of a sudden it will want to rotate. Since the point of action is 0.62 meters below this, then there'll be a lever arm of this against this given by this force, which will tend to swing the gate this way. And if you want to stop it, then you need to apply some force here. So that's basically the question that's being asked of you. What force do we need to apply to keep the gate shut? And so all we need to do is take moments. So if you look at the sum of the moments, we have a force it takes to keep it shut multiplied by its lever arm. The lever arm has to be 5 meters. In the other direction, we have a force that's trying to open it. The lever arm for this has to be 0.625 meters. Just trying to prove how clever I am, that I can do math in my head. And so this we know. This we know, obviously, this we know. The only thing we don't know is this. Then we can solve for that. And it turns out to be 1,000-ish kilonewtons that we'd have to apply to keep it shut. And that's it. So don't overcomplicate things. Remember the rules that we have. We have to calculate a force that acts. Force is equal of the resultant force is unit weight times the area multiplied by the vertical depth of the centroid of the plate, T. If it's inclined, the vertical centroid of the plate is just this height. We want to know where it acts. we use this second moment of area formula. The coordinate system for that has to be x on the surface, y in the plane of the planar surface. It can't be curved. It has to be planar. It can be any shape. The distance to the centroid is the slope distance from the surface to the center of this plate. And if you can calculate that and the second moment of area of the plates, you can get everything else you need to be able to calculate the where the resultant acts. Once you know where the force and the resultant act, then you have enough information to be able to look at a failure mode and calculate some interesting feature about it. Whether it's the top blowing off a Comet airliner or the Aloha 737 going from Hawaii to the islands of Hawaii, or these kind of hydraulic structures, then you have to define a failure mechanism to resolve either moments or resolve linearly in x and y. Okay. So we've taken this result for granted, so I'm not going to go through that. This is kind of a useful diagram, maybe. This is just the things we've talked about to define exactly what these components are. The centroid of this we can get from these standard shape theories. The distance to the center of pressure is measured, and the slope distance, and the distance to the centroid is measured vertically. So that's one thing I'll add, I guess, given by this thing here. Yes, this is actually useful, right? So YC is the in-plane distance to the centroid, and H sub C is the vertical distance from the centroid to the surface. And if you remember those things, then everything will be wonderful in this class. Okay? All right. Well, let's go through a slightly more challenging question, very similar to the one before. Yeah, so we'll finish off on this one. So you have a slightly more complicated geometry. I won't go through the calculations, but we'll just talk about how to do it. What do we have? Well, we have a gate that hinges around here. We want to know what kind of force we have to apply to keep this gate closed, and that force is P, and that's basically the question. We have some dimensions of this wall: 4 meters down, 2 meters across, I think 3 meters into the page. And so if you look going in this way, this is 3 meters. I won't draw it here because it'll make it complicated. And if we look at this vertical wall, you can imagine that the pressure distribution looks like this. And we'd like to know the force F1. And if you look at this bottom wall here, you could imagine the pressure distribution if we look at all these little pressure lines here. Actually, it doesn't look like this, does it? It's going to have a portion on it here which is added to that. Let's be clear about this. Because the pressure here isn't zero because it's below water. But the force acting here is going to be equal to this. And this is going to be F2. And I've kind of destroyed my F1. So the important thing about drawing this is that it will not be at 2/3 of the height. 2/3 not, I guess, right? So we have to remember that. So let's go through the quick calculation to do this. So let's calculate what F1 is. F1 is equal to the unit weight, the area of the plate, times the depth of the centroid. The centroid is the centroid of this plate. So this is H sub C. H sub C is going to be 3 meters, and the centroid is halfway down, so this is 2 meters, so it's going to be 3 plus 2. They're doing F1. Yeah, okay. So this is here 3 plus 2, H sub C. And this is the area of the plate, which is 4 meters tall by 3 meters wide. 3 by 4. And so the force comes out to be 5.9 times 10 to the 5 newtons. The centroid of this plate, where is it? This is the centroid, right? I can't draw it so well, but it's just horizontal. So it's 2 meters this direction, 3 meters this direction. It'll be right in the middle. It's about the right size piece of paper. And so the centroid will be physically in the plane of the plate. And so the centroid has to be this depth, h sub c. So what's that? H sub c is going to be 3 meters plus 4 meters. So this is h sub c. This is the unit weight of water. And this is the area of the plate. 2 meters in this plane and 3 meters into the page. So we have both the forces that are acting on the structure. So to be able to solve this problem, we're going to need to take moments about a point. This point is going to be here. So we need to know where this acts, and we need to know where this acts. Bottom one's easy, right? It's a linear distribution, so nothing varies. It's going to be dead slap in the middle. You could do the calculation to figure it out, but you know that if the distribution of pressure is like this, uniform across it, by definition, it has to balance about this middle point. And so the location of the centroid is, so the point of action is going to be here, which is going to be 1 meter in. So that's just by inspection. The other one, we can do our location based on our parallel axis theorem. We need the second moment of area about the centroid. We need the location of the centroid and the area. Location of the centroid, in this case, is here. So y is vertical, and it's going to be 3 meters plus 2 meters to get to this point, right? This is also the location of y sub c. So this should be 5. 3 plus 2 is 5. The area of this plate is 4 meters down and 3 meters into the page. So this is area of plate 1. And by parallel axis theorem, is it behind? No, it's below us, right? So this is this expression here. A 12th times the width of the plate multiplied by the depth of the plate cubed. Let's get this on here. 1/12 times the width of the plate times the height of the plate cubed plus the depth of the centroid. So this is just this expression here. And what comes out of it is that the depth of action is equal to the centroid of the plate plus a little bit. And that little bit is 0.27 meters. So this would be the centroid. And this is 0.27 meters below it. Okay. And then, so we have the forces by magnitude. We have the point of action of both the forces. And so now, if we want to look at failure, which is separate from all of the stuff we've done before, we have to resolve around some kind of failure mode. The failure mode is that the plate's here. We've got water pushing down on it to kick it out. We've got water pushing on the side of it to kick it out. So it's going to net move in this direction. And so we restore it by applying this force P. And so we just take moments around the top. And if we take moments around the top, then I guess let me make this smaller so it all fits on at the same time. Then we just have this. So let's see. F1 multiplied by L1. Okay, so yeah, so this is 5.27. It's 3 meters to get to this point here. So this point here is going to be 2.27, right? To this point here is 2.27 meters. So this is L1 times F1. So F1 times L1 is counterclockwise. F2 times 1 meter is also counterclockwise. And it has to balance with the restoring force, which is going to be this force P multiplied by its lever arm, which is the height of this, which I think is 4 meters, right? And so P times 4 meters. And so we know everything in here except for this one thing here. We don't know what this is. So that's our 1 known. One equation, one unknown. If we rearrange it, we solve for the magnitude of the force we have to apply. And it's a force that's applied to the total system. And so when you think about this, you will have to think about it in a week's time for the assignments. Remember these three things. Magnitude of the force, very simple expression, which is defined by the height of the centroid of the plate below the surface. The location where it acts, which is defined by the length in the plane of the structure that you're looking at. And then if you want to look at how it fails or how it behaves, then you resolve around a point that's not a random point, but says something about how this thing would actually physically fail. And in this particular case, the failure mode is by rotating around this hinge by definition. So that's it. So I'll leave it at that.